Okay, logistic regression time. First things first, we're gonna use our library, read Excel, and we're gonna open up our data set here. Cool. You can see we pushed our data set into excel.data. It's a data set about enrollment. So we have our outcome variable here, enroll, which is either a 0, which is not going to enroll in school because they're too cool, or a 1, which you can't see here, but these dots imply that there are more things, and there are ones, trust me. And that would be the people who are going to enroll in school because they are also cool. They're the real cool ones because they're in school. Cool. And then we got 4 predictor variables here: atmosphere, cost, infoscad, course car, whatever that means. Cool. They're continuous, which is nice. And they're going to tell us if our students are going to enroll. So that's going to be cool. So yeah, logistic regression, what we're trying to do here is that we have a dichotomous outcome variable. And so you're going to have a 0 or 1, either going to go to school or you're not. And we're trying to look at predictors of people going to school or not. Cool. That's why we use logistic regression, dichotomous stuff. Anyway, to make things simpler, we're just going to go ahead and push our outcome variable into a thing called outcome, a variable called outcome, and then all of our predictors into predictors 1 through 4 so that we don't have to pretend like we know what we're talking about. Bam, there we go. Now we just got outcomes and predictors, and this is good to note that when you do this, you can use all of the syntax, and it doesn't really matter what your data set is as long as you attach it properly and all that jazz. You can put anything into these, and the entire rest of the syntax will run all of the logistic regression procedures for any data set as long as all those variables meet the requirements that you need. Speaking of requirements, one of our requirements is that our predictor variables are not correlated with each other higher than 0.4. So I did this individually instead of doing a correlation matrix. You could do that as well, but I just correlated each two. Scouts going outside. Every pair of predictors, I just correlated them. So let's run that though, or delete it, or we can run it. Boom. Yep. 0.09, 0.35, 0.12, 0.21, negative 0.01, 0.08. Looks like none of those are bigger than 0.4, so we're good to go. Right on into the logistic regression syntax. This is just a simple logistic regression with outcome as our outcome and one predictor, pred1. Then we're gonna go family binomial link logit. That's just gonna say, hey, we're doing logistic regression in this GLM function. So yeah. Hey, look, I'm waking up at 9 hours. Let's go ahead and run that. Boom. Yay, it ran. Yay, R has a model 1 now. Oh, that's hard to understand. Okay, cool. Let's run summary model 1. Put that into something more readable. Bam. Cool. We've got some outputs that actually make some amount of sense. You can see we called our GLM formula, which I just explained. It's a little bit different, but whatever. It's the logistic regression with the outcome, which is actually enroll, but we pushed that in there, and pred1, which is one of the predictors. I don't remember. That's why we pushed it. Cool. So here you got your estimates and your z values. That's cool. Then you also have your deviance values. We're we're going to use that. We're testing the chi-square test in a little bit. So let's go ahead and do it. So chi-square test is what we use to determine basically if the model is significant or not. To do that, we're gonna go ahead and push this, which is just referencing model, so degrees of freedom null, that's actually just this number right here, right? 174, but we're calling it this nomenclature so that we can push it into chi-squared degrees of freedom 1. It's just going to be the degrees of freedom for our model 1. That's going to be useful for us later. And it's going to be minus the residual degrees of freedom. This is going to be 1, but now we have it in chi-squared degrees of freedom 1. And I did it again. Let's go ahead and control enter this time. Should be 1. Cool. So now we have our chi-squares degrees of freedom. This is just going to tell us our n, which is kind of a cool trick, I guess. You count the rows if you have all of the data. If you have no missing data, then your n is the number of rows in your Excel sheet. So yeah, 175. That's cool. We don't really need it though. I don't really know why it's there. Anyway, we're gonna calculate our chi-square for our model 1, which you compare the deviance of model 1 to the deviance of the null model. Again, these are things we had here. It's deviance of the model, so deviance of the null. So let's go ahead and run that. Control enter. And we got that pushed into our chi-square 1 thing. You can see right here, 0.0399, whatever. Cool. So is that significant? We're going to run our little function here. To get a p-value, a piece chi-square. We're going to use the arguments of the chi-square value we just calculated and the chi-square degree of freedom value we just calculated. This is actually just 1. Actually, it's but whatever, we'll be deliberate in what we're doing, and you have to have 1 minus or else you're not going to get a interpretable p-value. Control enter, bam. Looks like we didn't get an interpretable p-value anyway, probably because I didn't highlight everything. Good. That's not good. It should be significant, I thought. Maybe it's not supposed to be yet. Well, regardless of what I think it's supposed to be, this is clearly not significant. This is a 0.84. That is certainly higher than 0.05. So, not significant model. Wah, wah, wah. Which means we don't really need to calculate these odds ratios, but sure, let's do it anyway. Boom. Oh, and what is this doing? Good question. It's exponentiating the coefficient of model 1, and that's going to give us our odds ratio. So this means that the the intercept accounted for more increase in the odds of someone enrolling than did predictor 1, which is probably why it wasn't found to be significant. Cool. We can look at the CIs for the odds ratio. Yeah, so those pop up right here, and you don't want those to, basically the way you know if it's significant or not is if it includes 1 inside of the CI. Both of these do. Again, the model was not significant, so that's not a surprise. Neat. Let's do a multiple linear regression now. It's going to be basically exactly like the first one, except it's going to be called Model 2 because it is the second model. And it's going to have a lot more predictors. Predictors 2, 3, and 4 are going to join the party now. Remember that they used to be, or it's not that they used to be, but they are associated with these three. I just pushed them in earlier so that I wouldn't have to talk about what was in Excel data again, but for some reason I feel the need to talk about it. Anyway, Scouting. Sorry about that. We're running on almost 11 minutes, so this is probably going to be a 2-video set, so that's cool. Let's go ahead and run our multiple linear regression. Not linear. It's not linear regression. This is a multiple logistic regression. That was a test to see if you were paying attention to my video, and if you caught that, then congratulations to you because you were paying attention. Multiple logistic regression. Running that line. Cool. Now we got our Model 2 up here. Oh no, that doesn't make any sense. Let's run a summary. This is like, cool, we got some of the same stuff that we got the first time. That's neat. But wait, we got stuff for all the predictors, which is cool. And look, some of them are even significant this time. Particularly this predictor 4, which is like bonkers big. So that's cool. That's pretty much the only difference you're going to see in this output. You're still going to get your deviance that you expected, residual deviance, all that jazz, but now we have more predictors and their estimates popped out. There's z-values, and of course there's significance of the z-values. So now we got some significant predictors. Looks like predictor 2 was, and predictor 4 was. Well, let's look at the chi-squared to see the overall significance of the model. We're going to call that one chi-squared 2. Because for model 2, did I run out of time? No, I did not run out of time yet. Cool, so we have chi-squared 2, or it's the same thing. You're just pushing the difference between the residual degrees of freedom and the null degrees of freedom into chi-squared 2. And yeah, so we expect that to be 4. Yeah, that's a 4. Cool. We're looking at the number of data again for no reason. And we're going to calculate the same kind of chi-square, the actual chi-square, by taking the deviance and subtracting it from the null deviance, pushing that into chi-squared 2. Boom, we got a pretty big change in deviance this time. So let's see if that chi-squared distribution is significant by running the same thing, except this time we're going to use the change in deviance, the chi-square statistic for Model 2 and the degrees of freedom change for Model 2. So the chi-square degrees of freedom. Let's run that. And bam, a really tiny number that's a lot smaller than 0.05. So significant chi-square distribution. So this model is pretty good. Cool. Yeah. So we can look at odds ratios and they'll actually matter this time. That's cool. Let's go ahead and run that. And let's run the CI too. Boom. So now we have some things. A lot of all three, or predictors 1 through 3 were smaller than 1. So that means they're basically like they lower the odds, whereas predictor 4 increases the odds by about 3% of someone enrolling.